I have a whole course on Introduction to Oceanography, where I do this, as well as the Ocean Atmosphere Dynamics course, where I do lots of the circulation aspects. But for continuity, of course, we will have this in use Peters one figure. We'll come back to more details as we go on with the dynamics, of course. This is the upper ocean circulation map for the global ocean, as well as the Indian Ocean, and this is the orography shown here with the Andes Mountains, the Himalayas, African highlands, and so on. The circulation looks complicated, but there are many relations to the winds themselves. Only complication that is really important is the fact that while winds can go across the planet, climb the mountains, and come down on the other side, when the winds drag the ocean, the land boundaries begin to create interesting dynamics for the ocean. The most important thing there becomes that the Coriolis again increases, zero on the equator increases to the poles. That creates what is called the western boundary intensification in the oceans. So let's look at the simple things first. You have the southeasterly winds and the northeasterly trade winds in the low latitudes. So you see those winds create these along shore currents, so-called Peru current here and the California current here. Similarly, you have Canary current, Benguela current on this side, and in the Indian Ocean it's a bit complicated, as we will see here. Interestingly, that dragging of the water by the trade winds creates a north equatorial current, which is consistent with the direction of the winds from east to west, and a south equatorial current from east to west. In the middle, you get this equatorial countercurrent, which is there in both these oceans as well as in the Indian Ocean. You can see here equatorial countercurrent, at least strongly in this season. How is that created? Because of the boundaries, as the winds drag the ocean and pile up water on this side, there is a gravitational downflow from the piled up water, which again, because of Coriolis, is pushed to the right, hits the equator, because you cannot cross the equator in the ocean easily, because Coriolis changes sign and vorticity has to be generated or destroyed to cross the equator, which tends to happen at the western boundaries. Okay, I'm rushing through these details, but as I said, there are related podcasts you can look at. So the trade winds generate these westward current. The mid-latitude westerlies create these eastward currents, and the boundaries close the loop by creating strong, warm western boundary currents taking the tropical waters to high latitudes, and then slow, broad, shallow eastern boundary currents bringing cold water south. So this gyre, if you add your Coriolis, water has to move north to the right of the direction here, to the south to the right of the direction here, and pile up in the middle. So in fact, sea level will rises by about 2 meters if you go from the tropics to the middle of the gyre. Okay, why is there western boundary intensification? It turns out that the winds, by churning the ocean, are putting vorticity or rotation into the ocean, rotational tendency into the ocean, and because Coriolis increases with latitude, the tilting to the south here is stronger than the tilting to the north here, so there is a net southward flow, and if you don't take that water back north, you're going to keep putting more and more water towards the south. So to balance this vorticity put in by the winds and the southward transport created by the winds, Coriolis, you need to generate opposing vorticity somewhere and take the water back north somewhere. And you can go through the mathematical arguments to show that that only can happen in the western boundary. You cannot do that in the eastern boundary. So eastern boundary has a southward flow, which is in the same direction as the interior flow, so that's not satisfying mass balance. whereas in the west you have strong northward flow with the proper sign of vorticity to balance vorticity put in by the winds. It's a very short explanation, but you can follow up on more details. So in the north of to the north of the subtropical gyre, so you have a subtropical gyre here, 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 and here. You have subpolar gyres, which is complicated here, but it's simpler in the Pacific. Unfortunately, it's split in the middle, so you cannot see it. So just remember trade winds, north equatorial, south equatorial currents, equatorial countercurrents, eastern boundary currents, western boundary currents. So you have the Gulf Stream here, you have the Kuroshio, Agulhas, Brazil current here, and eastern boundary currents like Canary, Benguela, Peru, California, and the Lewin current here is different because there is warm water coming from the West Pacific into the Eastern Indian Ocean, which creates a different kind of dynamics here. The warm waters that are being brought north here by the Gulf Stream into this Greenland, Iceland, Norwegian Sea region actually creates massive differences in the weather and climate between let's say this part of North America versus this part of Europe. Because of these warm waters, the weather is very mild here, and temperatures here can be 30-40 degrees colder than at the same latitude here because of these maritime effects. Okay, and the warm waters coming up here also have an impact on the atmosphere, warming it, increasing evaporation, and creating heavy waters here, the so-called North Atlantic deep waters, which sink and generate a so-called thermohaline circulation, which we will touch on a little bit later on. So Kuroshio is the western boundary current here, Oishio is the northern western boundary current. So you have a northward and southward western boundary currents. So Labrador, Gulf Stream, Oishio, Kuroshio, Agulhas, and Brazil here. Okay, what else can I say? Indian Ocean is different because you have the southwesterly winds in the summer months and northeasterly winds in the winter months. So you have two little gyres in the northeast winter monsoon, northeasterly winds producing different circulation, and the entire tropical circulation looks very different compared to the summer months. We had the strong Somali jet driving alongshore currents and upwelling, so that creates a broader gyre circulation here with the southwest monsoon current here, which is opposite to the north equatorial current here, because during the northeast monsoon these become almost like northeasterly trades. There are southeasterly trades here driving the south equatorial current and the south equatorial countercurrent, whereas in this season you get the entire southwest monsoon current circulation with the south equatorial current going way south here. So just keep these things in mind. Okay, this is a very brief introduction to ocean circulation, but we will come back to details later on. What becomes critical is how these are related to the sea surface temperature distributions, the turbulent exchanges between the ocean and the atmosphere, the heat content that's available to drive convection, cyclones, Madden-Julian oscillation, and all these kinds of time scales as ocean-atmosphere phenomenon in the coupled climate system. So many interesting things, and there is an exchange here called the Indonesian through flow, which goes from the West Pacific into the Eastern Indian Ocean, which creates many interesting time scales, spatial scales, ocean atmosphere interactions, and so on here as well. So all those things we will look at as we go forward. Here it's just an introduction to the climatology, so just remember and read up the book. It's done very well, so hopefully the podcasts help to reinforce the concepts.